Okay, so thank you, everyone. So today I'm going to present some work that I've been doing, not alone at all. So I have to acknowledge all of the people who have been working with me, especially Anta Clarissa, because we've been working a lot to create these paleogeographies, and also Frédéric Fruteau, Yannick Donadieu, Niels Meyer, Guillaume Dupont-Nivet, Mustafa Kaya, and many more people. So the aim of our work, when I was doing my PhD, I was working on the Asian monsoon around the Eocene or Oligocene transition. And so we wanted to check out a bit more throughout the Cenozoic what was happening. So I'm going to present you some results we have from the late Eocene to the late Miocene, and the response of climate and the vegetation cover to paleogeography changes. So just to give you a quick reminder of the monsoon system. So in winter, we have a widespread Siberian high pressure that is developing on Mongolia, for example, and Siberia, which is driving anticyclonic wind around Asia. And you have the migration of the jet stream that you see here in dotted line south of the Tibetan Plateau. And in summer, so you have a reversal of these winds because you have a widespread low pressure cell that is developing on the Asian continent because of a really warm temperature there. And so you have advection of moist air from the Indian Ocean mostly, and also a bit from the Pacific and the South China Sea towards the continent. So, and you have also the jet stream that is migrating north of the Himalaya and the Tibetan Plateau during summer. And this is yielding a lot of precipitation, so especially in India and Eastern China. So to understand a bit more why you have this so peculiar system that is developing, a lot of models have shown that you have a strong contribution from continentality, from different orogens in Asia, but also in the periphery of Asia. So you have Eastern Africa and, for example, Anatolia or the Hindu Kush or Mongolia, which are usually landforms that are much less explored than the Himalaya and the Tibetan Plateau when looking at the history of monsoon onset through time. But we have a lot of new fossils that have been found, especially in China and Myanmar, that are suggesting that we may have really strong precipitation seasonality as soon as in the Eocene, so where you have these yellow stars on the map. And this is a bit tricky because most of the mountains in Asia and Eastern Africa were not uplifted or not so much uplifted during the Eocene. So it kind of questions, do we really need orography and mountain to get a full monsoon developing at this time? And so we are going to try to reconstruct this history with paleogeographic reconstructions that have been built based on some paleogeography reconstructed by Fernando Poblete with Guillaume Dupont-Nivet. And with Anta and I, we have made different sensitivity tests to try and understand the respective impact of each mountain ranges on the climate. So I'm just going to present here a timeline of what could have been the orography evolution from the late Eocene to the latest Miocene in Asia. And also I put you some of the main boundary conditions that we have tested. So where you have a small white star, it means that we have been doing some tests, for example, removing a mountain or changing its shape or changing its altitude and check what happened. And we also, of course, tested a different configuration for the Parathetis Sea, which is which you can see on the western part of the map. That is lately becoming what we know at the Black Sea, for example. And it was a much wider sea that was connected to the Neothetis Ocean during the late Eocene. And so you can see the configuration of Asia during the late Eocene was less continental, and you had much more water all around, surrounding what is going to become India and Asia. So we did a compilation of 5 reference paleoclimate simulation with 5 reference paleogeography that you can see on top. And we also did about 15 sensitivity tests. So as I said, changing some of the parameters. And I'm just going to walk you through quite quickly on the big picture of the results. And then we're going to check out some of the sensitivity tests to try and understand what are the drivers. So in terms of precipitation seasonality, where you have the red dots, so what you can see shaded is the mean annual precipitation amount. So we probably have a dry bias over India for the late Eocene simulation because it's simulated as really dry, and it's probably not the case. Although we have shown that with a different orbital configuration, we could drive much more water advection on this region. But just focus more on the red dots, which are the regions where we have a monsoon-like seasonality, such as defined today, with almost like 70% of the precipitation that is falling during summer and really dry winter season. So we can see that this high precipitation is actually getting more and more widespread throughout the simulation. And as soon as the middle Miocene, about the middle Miocene, like you have a widespread seasonality that could be compared to what we have today in terms of monsoon precipitation. Now, if we look at the wind patterns, and what you can see in shading is sea level pressure. So where you have some blue, it's a depression. So it's what is driving the advection of moist air toward Asia. And as you can see, in terms of Somali jet, which is a black arrow that I've put it on top, we actually have a really shy Somali jet that is developing in early Miocene, but it's actually getting more and more important and stronger as soon as the middle Miocene. So in terms of precipitation, seasonality, and circulation, we can already see that the seasonality was widespread earlier than the atmospheric circulation that we see today. And when we look at winter time, so in red, you have the sea level pressure. So here you can see like we are actually tracking the development of the Siberian anticyclone. And it's actually only developing in the latest Miocene, where you see that you have these winds that go up to Siberia and are then advected toward eastern China, which we cannot have from the Eocene to the early Miocene. So the Siberian high was more likely pretty recent. In terms of vegetation cover, so I've used a biome classification from Peel, and I've tried to write like with the corresponding color the main biomes that we can see on the map. Otherwise, it's a bit complicated. But basically, where you have red and orange, it's dry or savanna. Everything that is in blue is going to be tropical, so tropical rainforest, monsoon, or tropical savanna. And in eastern China, you're going to have a mixture of biomes showing temperate features. And especially what is interesting is that you can see the more and more widespread biome temperate dry winter and cold winter. So the light green and the lavender biomes, which are actually maybe a good way to track the inception of a Siberian high. And we're going to try to see with some sensitivity tests how they arrive and what are the drivers. So the plots for the sensitivity test are a bit full, so I'm going to try to explain what's happening on this. So we've tested, for example, the Arabian platform raised above the sea level. So you can see on the map, especially on the bottom maps, that on the left map, you have a big part of the Arabian platform that is below sea level. And we have taken it out of sea level on the left test. And this is simply because the Arabian platform was really low elevation during most of from Eocene to Miocene, and with significant sea level modification during this time, it's very likely that it has become flooded, partially flooded, and then that has risen again above sea level, probably many times in the Cenozoic history, although it's pretty badly constrained in terms of fossils. And so we've try to see what was the main impact of Arabian platform rays. And what you can see in terms of, for example, winter and summer precipitation differences, it's like when you raise the platform, basically you're going to increase precipitation seasonality because you're going to lower the winter precipitation and increase the summer precipitation over Asia. And so this is what you can see with the magenta, the pink dots on the map. So everything that is pink is showing you areas where you have more precipitation seasonality with the Arabian platform going out of the sea. And so, of course, this is mainly due to the fact that you increase the continentality of the area, and it's going to reorganize the pressure patterns, and it's especially going to widen the low pressure band that you are creating during summer. And so you're going to drive more advection of moist air from the Indian Ocean towards Eastern Asia. And well, in terms of biome, you can also see like a spreading of like savanna or tropical savanna biomes on in India, for example, toward the west. And if we look at the Iron Plateau uplift, which is something that we see more and more in sensitivity studies now. So you can see on the bottom map, it's highlighted in white, the mountain chain that we have taken out and then uplifted. So the main effect of the Iranian Plateau uplift is going to block the advection of moist air that is coming in summer. And so you can see the big summer precipitation anomaly on top in the center, where basically you are trapping all of this moist air, and it's going to yield much more precipitation, especially in India, but also a bit in Eastern Asia. And this is going to yield as well an increase in precipitation seasonality, also because when the plateau uplift, it's also going to drive drier winter in India, because simply you are blocking the advection of westerly moisture toward the south in winter. And in terms of biomes, so I'm probably not going to detail everything, but well, you can also see some changes. For example, it's going to drive more water advection, for example, in the Tarim region and it's the Gobi deserts area. And so you can see a bit of differences in between biomes, but I'm not going to go too much into details for this one. Then we have tested also the Tian Shan and Pamir mountains that you can see in white, again, like on the bottom left corner. And well, these mountains are pretty interesting because they are on the path of westerly moisture. And actually what they're going to do is capture all the moisture that is coming from the westerly flow. So you can see a big blue anomaly in winter and in summer precipitation. So everything is going to fall. I mean, you don't have much rain in these regions, but everything is going to be captured by the orogeny, and it's basically going to dry what is on the other side, so on the eastern side of the mountains. And so it's usually amplifying the drought that you can see in the Tarim Basin, but it's also going to lead to an amplification of cold, dry winter biomes in northeastern China that you can see in the white circle in the bottom right image, simply because it's also going to amplify the seasonality in this region. And regarding the effect of the Tian Shan and Pamir Mountain on Southern Asia, so it's a bit complicated to see and to say. I mean, here you can see with the black dots that all over India, we have a decrease in precipitation seasonality when the Tian Shan uplift, simply because it's going to deflect the westerly moisture in winter a bit in the north and a bit in the south. And so you're going to have a bit more moisture in India. But we could assume that providing the Iranian plateau had risen up to a certain level before the Tian Shan and Pamir uplifted as well, then you're going to have like this full blockage mountain range, and this may trigger different things in India. So I think it's really important to note that these are sensitivity tests, and we actually have no clue about the exact elevation of Tien Shan Pamir and Iranian plateau during, for example, the early to late Miocene. I mean, it's not well constrained to a point we could know which one was uplifted first and to which altitude. And we also have tested, I think it's the final test that I'm showing you. We also tested, which was something pretty interesting, the effect of the Altai and Engei Dome in Mongolia. So these mountains are pretty high. I mean, in Asia, you could figure they probably do nothing for for India, for example. But actually, it's pretty interesting because in winter, you're going to have a really strong effect simply because by uplifting mountains in this region, you're going to deviate the westerlies towards the north. And so you're going to actually widen the Siberian anticyclone because like the mountain you're going to have the snow albedo effect if they're covered in snow. So you're going to cool this region and amplify the Siberian high. And you're going to have also the barrier effect where the mountain is simply going to deviate the winds towards northern latitudes. And so the striking effect that we have with the uplift of the Mongolian landforms is simply that you're going to dry enormously northeastern China and northeastern Asia. And so you amplify the seasonality and you're going to have the big expansion of biomes typical of, today's biomes with a cold, dry winter that you didn't have before, simply because it's driving a much colder winter and much drier winter time. So we had a few other tests, on Eastern African uplift, for example, or with a Miocene Tibetan configuration, but I'm not going to bother you with more details. But so all of this is getting ready in a publication that is actually being reviewed now. And some of the main conclusion of the work was that the modern monsoon onset is most likely really diachronous and linked to paleogeography evolution. And it's probable that monsoon-like precipitation seasonality was already set in some parts of Southeastern Asia way before you had typical monsoonal winds that we have now. So it's not so surprising when you see all of the data that are coming up showing strong seasonality in precipitation. And usually it matches pretty well with what we have either for the Eocene or for the early Oligocene. So the two maps that you can see on the bottom with the red dots showing you where we have strong seasonality. So in a matter of conclusion for the wintertime seasonality, we could say that Tibet, Tian Shan and Mongolian mountains and continentality are going to be critical for typical East Asian monsoon onset. So they're going to act on different features, but they're going to be really important for this Eastern Asian monsoon. The Tian Shan and Pamir, so as I said, they will be pretty important for the jet stream summer migration, but we have to take them with caution because we don't have much information about their relative uplift with respect to Anatolian Iranian plateau. And so we also say that like the Eastern African origin, the Anatolian plateau, the Himalayan mountains, and the Arabian platform are critical for summer South Asian monsoon amplification. And as I said, like, for example, the Arabian platform history is really poorly constrained. So that would be actually really interesting to get more information on what is happening there. And so better timing in uplift history is paramount, and better constraint on elevation are critical because we probably have some threshold effect. We have been running tests when we lower the mountains. For example, if we lower them to 800 meters, you have really different patterns in terms of circulation. But as soon as they are about 1,200 meters, they start interacting with the global circulation, and then you can start seeing some interesting things. And so I've not talked too much about the PCO2, which is something, as Haiping said, is going to be critical in the future. So it's mostly because when we compare it to the effect of a full mountain uplift, the CO2 triggers less impact. But of course, I mean, for a modern problematic, a small change in CO2 is of course going to be have a huge effect simply because you have so many people living in these regions. So, I mean, this is really a paleo perspective, and I'm not trying to say that CO2 is not important for what we have now. Thank you for your attention, and I'm happy to take questions.